The Trident II D5 is one of the most consequential strategic weapons ever fielded, a submarine-launched ballistic missile (SLBM) that has formed the backbone of the sea-based leg of nuclear deterrence for both the United States and the United Kingdom for decades. Even for non-specialists, the missile's silhouette and reputation carry an aura. It's a weapon built for extreme range, reliability, and survivability, launched from hidden submarines that can patrol the world's oceans. In this review-style breakdown, we'll walk through what the Trident II looks like, what's inside the missile that makes it function, how it performs in operational terms, and what it costs, all presented in plain English for viewers curious about one of the most powerful pieces of military hardware on the planet. When you first picture a Trident II, imagine a long, smooth cylinder built for underwater launch and flight through atmosphere into space. The tactical appearance is deliberately unflashy, a tall slender tube roughly the diameter of a small car tire and stretching many meters in length. The exterior is engineered for harsh environments, salted seawater, extreme pressure at launch depth, the violent shock of cold launch from a submerged tube, and then the searing heat and aerodynamic stresses of hypersonic flight during boost and reentry phases. The missile is normally stowed inside a submarine's missile tube with a protective canister. The outer skin of that canister and missile features corrosion-resistant coatings and thermal protection, with attachment points for handling and interfaces for the submarine's fire control systems. Externally you'll also see control surfaces, aft fins that deploy after boost for in-atmosphere maneuvering, and fairings around the nose cone that protect the re-entry vehicles during ascent. The overall look is one of efficiency. No wasted ornamentation, everything designed for a specific function and to survive extreme conditions. Under that skin, the Trident II is a three-stage, solid-fuel rocket. Solid propellant was chosen for robustness and long-term storage stability, qualities required for a missile that may spend many years aboard a submarine in ready status. Each stage is a precision-manufactured composite and metal assembly containing a carefully formulated propellant grain, internal insulation, casings that withstand high pressures, and mechanisms that dispense thrust in a controlled burn. The stage stack is arranged axially. First stage booster at the rear, second stage in the middle, third stage forward. After the third stage completes its burn, the missile reaches velocities sufficient to inject its payload, the post-boost vehicle and re-entry bodies, onto a ballistic trajectory toward the target area. Inside the forward section sits the post-boost bus and the re-entry vehicles. The post-boost vehicle is essentially the missile's delivery manager, a precision guidance and propulsion package that can perform attitude adjustments and small velocity changes, allowing the missile to deploy multiple warheads at pre-programmed trajectories. Trident II historically supported multiple independently targetable re-entry vehicles (MIRVs), enabling one missile to place multiple warheads on different targets across a wide footprint. Those re-entry bodies, protective cones that shield nuclear warheads during the violent re-entry phase, separate from the bus and streak down toward their targets at hypersonic speeds. Materials used in these components are chosen for thermal resistance and structural integrity under re-entry loads. Guidance is one of the most tightly guarded and carefully engineered aspects of any strategic missile, and Trident II is no exception. It uses highly accurate inertial navigation systems, backed by sophisticated onboard computers, that keep the missile on a precise trajectory through boost, mid-course, and pre-deployment phases. Over its service life, navigational upgrades have improved accuracy through better sensors, refined algorithms, and integration with additional navigation aids. The result is a missile that can place re-entry vehicles on precise impact points thousands of kilometers away, accuracy that matters when deterrence strategy relies on credible, reliable strike capability. The control systems inside the missile are equally resilient. Actuators and servo systems steer thrust vectors and fin surfaces. Pneumatic and mechanical interfaces must function flawlessly after years at sea. Electronic assemblies are hardened against shock, vibration, temperature extremes, and electromagnetic interference. Power for electronics and actuators typically comes from reserve batteries that activate upon launch. Data buses inside the missile distribute sensor inputs and control commands. The software embedded in the guidance computer implements guidance laws, timing sequences for stage separation, and deployment patterns for re-entry vehicles. The propulsion packages are brutal and exacting machines. Solid rocket motors for each stage are manufactured with precise grain geometries to produce specific thrust curves. The first stage needs to give a large impulse to punch the missile out of the water and through the dense lower atmosphere, while second and third stages shape velocity profiles optimized for reaching the desired apogee and flight path. Manufacturing quality, propellant chemistry, and casing strength are critical. Any flaw risks catastrophic failure. Over the decades, the Trident II's motors and separation mechanisms have been refined to improve reliability and reduce risks of stage anomalies. From a performance standpoint, the Trident II D5 is designed for extreme reach and operational flexibility. Published performance summaries characterize it as a long-range strategic missile capable of intercontinental reach when launched from submerged platforms. Exact range figures can vary with payload burden and flight profile, but in operational terms, the Trident II enables a submarine patrol to threaten targets across continents while remaining hidden under the sea. The missile is engineered for fast boost phase dynamics followed by a ballistic midcourse through exoatmospheric space and culminates in high-velocity reentry of the warheads. Reentry speeds place the bodies at hypersonic velocities, making interception once in terminal approaches enormously difficult. The combination of range, speed, MIRV capability, and submarine basing makes Trident II a potent element of strategic deterrence. Accuracy has always been a focus for strategic systems because better accuracy allows lower yield warheads and increases target effectiveness. Over its life cycle, Trident II benefited from upgrades to navigation, post-boost control, and reentry vehicle design that improved circular error probable (CEP), meaning the warheads land closer to the intended aim point. That accuracy supports both military planning and arms control dialogues because it affects how many missiles or warheads are judged necessary to hold particular targets at risk. Another crucial dimension is survivability. Submarine-launched missiles gain their strategic value not only from technical performance but from the stealth and mobility of their launch platforms. Ohio-class submarines in the U.S. Navy and Vanguard-class submarines in the Royal Navy carry Trident II missiles deep under the world's oceans, quietly moving, hiding, and presenting an assured second strike capability. A nuclear force that can survive a first strike and retaliate is the essence of a credible deterrent, and Trident II's integration with ballistic missile submarines is what makes its strategic effect so profound. Historically, Trident II entered service in the 1990s and has undergone life extension and reliability programs to ensure it remains viable into the 21st century. Those modernization efforts include upgrades to guidance suites, replacement of aging components, and improved re-entry vehicle designs. Maintenance and refurbishment cycles are complex. Missiles periodically return to specialized facilities where motors, electronics, and casings can be inspected, refurbished, or replaced. These sustainment programs are essential to keep a sea-based deterrent operational for decades. Cost is always part of the equation. Strategic systems are expensive. Not only the missile hardware itself, but the submarines that carry them, the warheads and re-entry bodies they deploy, the command and control infrastructure, and life cycle sustainment activities. Published budget figures and defense analyses indicate that individual missile procurement costs run into tens of millions of dollars per round when counted purely as hardware. However, the broader program costs, development, life extension programs, integration with submarines, warhead refurbishment, and sustainment, are far larger. Life cycle costs are the major driver in defense budgeting decisions. Sustaining a sea-based deterrent for decades requires steady investment. That said, for nuclear strategy planners, the cost is weighed against the deterrent value, the diplomatic and security stability that a credible, survivable second strike force brings. Beyond raw numbers, there are political and strategic dimensions tied to Trident II. The missile factors into international arms control treaties, bilateral arrangements, and national posture decisions. For the United Kingdom, Trident II is procured under arrangements with the United States and fitted to British submarines, representing a key element of UK national deterrence policy. For the US, Trident-equipped submarines are a core leg of a triad that also includes land-based missiles and strategic bombers. Debates about modernization, replacement submarines like the upcoming Columbia class in the U.S., and warhead posture reflect complex policy choices involving costs, threat assessments, and alliance considerations. The operational safety and control infrastructure are also critical. Strategic missile forces operate under strict command and control procedures and multiple redundant safeguards to prevent unauthorized launches. Secure communications, encrypted authentication, and layered decision support systems are part of the human and technical architecture that ensures these weapons are only used under lawful and deliberate orders. These procedures are as important as the missile technology itself. They protect against mistakes, accidental launches, and unauthorized use. Technologically, the Trident II illustrates the intersection of materials science, propulsion chemistry, guidance engineering, and systems integration. Composite casings, high-energy propellants, radiation-hardened electronics, and advanced thermal protection for reentry vehicles are all parts of the puzzle. Manufacturing tolerances are tight and quality control is exacting. The missile's reliability record is a testament to decades of engineering discipline and rigorous testing programs. Ground firings, full-up system tests, and simulated launches refine designs and validate performance before operational deployment. From a public understanding perspective, it's necessary to stress the human and ethical weight behind such systems. These missiles are designed to carry nuclear warheads and thus symbolize existential, destructive power. Conversations about them inevitably touch upon deterrence theory, strategic stability, the ethics of nuclear weapons, and non-proliferation. For many policymakers and militaries, systems like Trident II are seen as deterrents that have helped prevent large-scale great power conflicts since World War II. For anti-nuclear advocates, they represent a moral and humanitarian challenge. Either way, any technical review exists within this larger civic and moral context. Looking forward, the Trident II family will continue to be sustained and modernized as long as submarine-based deterrence remains central to policy. Ongoing modernization programs will likely focus on replacing aging components, updating guidance hardware and software, and ensuring compatibility with new submarine classes and command systems. At the same time, arms control negotiations and strategic dialogues between nuclear-armed states will shape how many missiles and warheads are fielded, how they are postured, and what limits or transparency measures might be applied. In operational terms, few weapons match the Trident II's combination of stealthy basing, long reach, high speed, and strategic impact. Its exterior gives the impression of functional austerity. Inside, a compact orchestra of stages, guidance systems, and reentry vehicles executes a performance measured in seconds and capable of shaping global strategy. Performance metrics, range, accuracy, survivability, are world-class, and the costs, while high, are judged against the high stakes of national security. The Trident II D5 is a technological achievement and a strategic instrument that has and will continue to influence global deterrence dynamics. For an audience interested in engineering, geopolitics, or defense policy, the Trident II offers something for everyone. It's an example of extreme engineering reliability, a case study in weapons system sustainment, and a focal point for debates about the role of nuclear arsenals in the modern world. Whether admired for its engineering or scrutinized for its moral implications, it remains one of the defining strategic systems of the modern age.